So we'll have a review for your bimonthly. And what did we have for our bimonthly? It's just carbohydrates, di ba? Just carbohydrates, no? Structure and function, and then metabolism. Okay? All right. So, carbohydrate structure. You know what the carbohydrates are, no? They are compounds that usually contain ketones, ketone group or aldehyde group, and a number of hydroxyls. No? They are described as polyhydroxy alcohols because there are so many hydroxyls. So polyhydroxy alcohols, a derivative of an aldehyde or a ketone. Okay. So you categorize your carbohydrate according to the number of saccharide molecules it contains. So the simplest is monosaccharides. Then you have your disaccharides. Then you have your oligosaccharides. And then, of course, your polysaccharides. Now monosaccharides are also being categorized according to the number of carbon atom it contains. So the simplest monosaccharide would be containing 3 carbons. You cannot have a monosaccharide with 2 carbons. So it must always be 3 because it says polyhydroxy alcohols. No? And you need at least 2 carbons to contain your hydroxyl. So to make it poly, because that's more than 1, no? And then you have the other carbon to be an aldehyde or a ketone group. No? So that's number 3 carbons, then 4, then 5, then 6, then 7. We end up at 7 for naturally occurring monosaccharides. Up to 7 only. If there are monosaccharides that are more than 8 carbons, or more than 7 carbons, they are made in the laboratory or they are synthetic. Okay? All right. So we call our monosaccharides as the simplest carbohydrate. And they can belong to the D series or L series. Okay? No D or L. So you know that. What is your D or L? It all depends on the D or L is the arrangement of the hydroxyl and the hydrogen on a particular carbon. And that particular carbon is an asymmetric carbon far from the aldehyde group. The farthest asymmetric carbon from the aldehyde group or ketone group. Okay? In that case, in glucose, that would be the 5th carbon. You in a straight chain formula, you number the carbon starting from the aldehyde 1, 2, 3, 4, 5, 6 up to 7, 6. Sorry, up to 6. And the 5th carbon determines whether it belongs to the D or L series. Now, in a straight chain formula, the D is where you have the hydroxyl on the left side and the hydrogen on the right side. That's the D. Oh, D is dextro. It should be, I'm sorry. Now, looking at it, it's on the left side. No? Looking at it, that is on the left side. It is on your left side. Oh. But for the compound, it is supposedly on the right side of the compound. No? But looking at it, it is on the D, or on the left side. No? That's the D series. And your L is on the right side. You're looking at it. Okay. Then we have stereoisomers. I know you know these things in your organic chemistry. Stereoisomers. Stereoisomers have the same chemical formula, but they differ only in the spatial arrangement, space, no? Or they are arranged in space of their substituent groups. So what are the substituent groups? Aldehyde group, ketone group, hydroxyl group. That's the one that you find, no? Now, what about enantiomers? Enantiomers. They are stereoisomers that are mirror images of each other. Mirror image. Oh, okay. Now, what about epimers? Epimers are still stereoisomers that differ in the position of the substituent groups at only one carbon atom. Like for example, glucose and galactose are epimers in relation to the fourth carbon atom. No? So they have the different arrangement there of the OH and the hydrogen, the fourth carbon atom for glucose and galactose. Also another one is glucose and mannose. Glucose and mannose, they also differ at carbon 2. Carbon 2. Okay, so those are just arrangement. No? Now, monosaccharides form rings. You have a 5-membered ring and a 6-membered ring. Diba? And they are called, a 5-membered ring is called furanose, a furan. And a 6-carbon ring is a pyranose. No? So when you say alpha-D-glucopyranose, so that means your glucose is in a pyran ring. Diba? All right. Monosaccharides can be joined by a glycosidic linkage to form disaccharides, oligosaccharides, and polysaccharides. So that is the bond between glucose units. Okay. Nucleotides also contain a pentose, a 5-carbon atom. So that is a furan, no? And they contain a glycosidic linkage in which nitrogen is involved. While the glycosidic linkage between sugars, like for example, two glucoses, it is an oxygen link glycosidic linkage. However, in a nucleotide, although it is still a glycosidic bond, but it is nitrogen link. All right. Carbohydrates may contain phosphates. So they are phosphorylated. You have seen that. Glucose 6-phosphate, glucose 1,6-diphosphate. Okay? Or they can be attached to amino acid. No? Amino acid. So you have they're attached to amino acids, then they become since amino acids are found in proteins, no, and also in a chain, so you call it glycoprotein. Or your monosaccharides can be attached to a sulfate. It is a sulfated monosaccharide. Your monosaccharides can be oxidized to form what you call sugar acid, or it can be reduced to form into sugar alcohol. An example of your sugar acid, glucuronic acid. Remember? Uronic acid pathway, glucuronic, no? Glucuronic acid or glucuronate. And then they are reduced and become alcohol. So sugar alcohol. You have sorbitol from glucose or fructose. You can get sorbitol. Then you have from ribose, ribitol, from mannose, mannitol. Okay? All right. So we mentioned that already. Although we usually illustrate your monosaccharides in a straight chain formula, remember they can also exist in a ring form. And the two ring forms are peranose, peran, no, or furanose or furan. Now, the I don't know how to show this to you, because if I have a blackboard, we are having a class face to face, I can write it in the blackboard. So, however, the peran ring or the peranose form of glucose can exist in two, and we have what we call a boat form and a chair form. Now, supposing this is your peranose. Okay? Now, when you are going to make a boat form of this, it will be like this. there. It looks like that way, no? You cannot see it. I do not know why the camera is, no? That's a boot form. When it is in chair form, it looks like this. Huh? Oh, never mind. Boot form or chair form. No. Okay. So more or less you have an idea of how your carbohydrate looks like. Okay. Now let's go to digestion of carbohydrates. The major dietary carbohydrates is starch. The major starch. So you can get starch from your rice, your corn, root crops, kamote, potatoes, no? So you have potato and sweet potato, no? That's our kamote. So those are sources of carbohydrate. And of course, fruits, banana, no? Papaya, okay? Now, another source would be disaccharides, like your sucrose, which you get from your sugar cane. No? It's a disaccharide. And then another source, while you're still an infant, would be the disaccharide in milk, and that is lactose. So how you have your starch, sucrose, and lactose. So these are the common ones. No? They are digested mainly to glucose, fructose, and galactose. You know that your starch is a polymer of glucose. So if it is totally digested, glucose is the product. How for sucrose, sucrose is made up of two monosaccharides, glucose and fructose. So the end product would be glucose and fructose. And lactose is made up of glucose and galactose. So digestion of that would bring about glucose and galactose. All right. So you start the digestion of your starch in your mouth. You have your salivary amylase. The salivary amylase is capable of breaking down the starch down to maltose level. Okay. Or maltotriose, or short oligosaccharides like those dextrins, no? Okay, maltose, maltotriose, and short or small oligosaccharides as a result of the digestion in the mouth. That is, if you give it time for your salivary amylase to act on your carbohydrates. But if you just you just gobble your food, you shovel food into your mouth, and then you just probably only once or twice you chew it, then you swallow it. So practically there is no digestion because you did not give time for your enzyme to act on the linkage, on the glycosidic linkage. Okay? And when that bolus of food that you swallow and it goes into the stomach, the environment there is not favorable for whatever salivary amylase that goes with the swallowed food. Huh? Why? Because it is acidic in the stomach. It is acidic. And we know already that your enzymes can be affected by the pH. There are enzymes that works well in acid pH. There are enzymes that work well in alkaline pH. And there are enzymes that works well in neutral surroundings or near neutral. Huh? Near neutral pH. Okay. So, in the stomach, actually there is no enzymatic digestion. But you can have a breakdown of some starch molecules because of the hydrochloric acid. And you know, your hydrochloric acid is around pH 1.5 to 2. No, you can see how acidic it is. And it can do what we call acid hydrolysis. Acid hydrolysis. Okay. But also, acid hydrolysis takes time to do that. So not all of your carbohydrate that you have swallowed will be broken down to your maltose or to your monosaccharide level. No. Okay? And then that food from the stomach is now channeled to the small intestine, wherein in the small intestine, especially the upper part of the duodenum, where pancreatic juice empties through the pancreatic duct, or the common bile duct because the hepatic duct and the pancreatic duct joins together to form a common bile duct which empties into the duodenum. Okay? The bile excretes a high content of bicarbonates, as well also as the pancreas also secretes bicarbonate. The idea is to neutralize the acid coming from the stomach. Okay? Coming from the stomach. All right. Now, together with that bicarbonates coming from the pancreas, we have an enzyme for the breakdown of carbohydrate from the pancreas known as pancreatic amylase. Very, very similar to your salivary amylase. They only differ in their location. Okay. So the pancreatic amylase now continues the digestion, and end products would be, of course, maltose, mostly maltose. No? Now, if you have taken sucrose, lactose, this pancreatic amylase cannot work on it. But you have enzymes now from the lining, or what you call the brass border of your small intestine. These are epithelial tissues or epithelial cells that produce these particular enzymes that act on these disaccharides. And we have sucrase for sucrose, and we have maltase for maltose, and we have lactase for lactose. Okay? So the disaccharides, maltose, sucrose, and lactose are fully digested into its component units. Maltose into 2 molecules of glucose, sucrose, a molecule of glucose and fructose, and lactose made up of glucose and galactose. Okay? And there, it is now in a form that can be absorbed. Absorption. Okay? And you have transporters there, several transporters. So glucose, fructose, and galactose are the final products generated by digestion of dietary carbohydrates. These monosaccharides are absorbed by intestinal epithelial cells. They are transported into the cells on carriers, moving down a what you call concentration gradient. So they are also moved into cells on transport proteins, which carry sodium ions in addition to the monosaccharides. This is a secondary active transport process. A sodium, potassium, ATP is pumped, sodium into the blood, and monosaccharide moves down a concentration gradient from the cell into the blood. Okay? So there you are. Your sugars now are in the blood. Now, there are carbohydrates that are not digestible for the main reason that we do not have an enzyme to break that particular glycosidic linkage. What are these indigestible enzymes? This is cellulose. Cellulose. You can get it from, they are usually plant-based. Leaves of plants. That's why vegetables are important. Fruits are also important because of this cellulose. Okay. They are what you call dietary fibers. Dietary fibers that passes through the intestine into the feces. And these fibers absorb fluids. And so this makes your stool soft and easy for elimination. Okay? All right. So these digestible fibers, indigestible fibers are very, very important. Now, especially also, these digestible fibers makes it hard for the absorption of cholesterol, dietary cholesterol. And so this dietary cholesterol, as long as there are intestinal fibers, not all of them can be absorbed. So that is, you are lessening or decreasing the amount of dietary cholesterol to be absorbed, which is beneficial, of course, because actually there is no need to take in cholesterol. It is just part of the diet of flesh, because you cannot find cholesterol from plants or plant-based. You only get cholesterol because the plant cannot form cholesterol. Remember, plant cannot form cholesterol. So there is no cholesterol in plant-based food. It is only animals that can form cholesterol. Okay? All right. Now, what happens when you have cholesterol in your the food that you eat? And if dietary fibers are there, in form of vegetables, of course, no, which are plentiful, okay? And this is, it hinders, the fibers hinders the absorption of cholesterol, okay? So it is important, therefore, that you will have dietary fibers. Now, if we are like the termites, if our digestive tract is like the termites, then we could digest cellulose. We could digest cellulose and made it into glucose. The enzyme there is cellulase. Cellulase. Termites does not have cellulase, but they have bacteria that is in a joint enterprise with the termite. This bacteria is in the intestine, the gastrointestinal tract of termites, producing cellulase. No? So it is a symbiotic relation between this bacteria and the termite. They produce cellulase. Now, we have also bacteria, but unfortunately, we do not have that kind of bacteria that the termites has. No? We have, they call it the microbiome, especially in the large intestine, divided into two groups, the good ones and the bad ones. You call it the good bacteria. Okay? And the bad ones, the bad bacteria. And you know what it means. The good bacteria is beneficial for us. Like for example, lactobacillus. No? Those who are who would like to take yogurt, it's full of lactobacillus. No? Yakult, yes. Oh. Lactobacillus shirota strain. Okay, so that's beneficial for us. Now, if we have that kind of bacteria from in which the termites are having, then I don't think we will have the people in the world will suffer from hunger. No? You can eat your notebook. No, not the notebook that you are using. No? The notebook, the paper one. Oh, you can eat that because that is cellulose. So anything that is cellulose, you can eat it. So the tree, where do you find the cellulose? Usually leaves. So you eat that. Now it's different with ruminants, which is grass. They ferment the cellulose. So they have fermentation going on in these ruminants. You know, carabaos. How many stomach is carabao has? Hala, nakalimtan ng comparative anatomy. What about the cow? How many stomach has a cow? Mga sir?
Four ba? Four ba to?
There are four. Four stomach joined together. One after another. That is your carabao or cow. Yeah? That is to ensure fermentation. They ferment the grass. Unlike the termites, they can eat wood. Wood is cellulose. And they can digest it because of the bacteria that lives there that produces cellulase. Okay? All right. So your monosaccharides now are in the blood. And let us now see how your glucose, which is the sugar. Now, by the way, you should remember, glucose and fructose are what? Epimers, no? They can be easily transformed into each other. So one into another, like fructose, or the fructose becomes glucose. So it is easily through an epimerase. And we have enzymes that transforms it. Even galactose is an epimer also of glucose. And it's just a matter of the position of what carbon atom. No? Okay. So you have mannose that can be transformed into glucose, galactose into glucose, fructose into glucose, or there is even a pathway for fructose itself, which bypasses some of the steps in glycolysis, but still utilizes the rest of the pathway of the glycolysis. Okay. So we start with glycolysis. The pathway which oxidizes glucose into pyruvate. And it all depends now whether there is enough oxygen or none, or deficient oxygen. If there's plenty of oxygen, then that pyruvate is converted to acetyl-CoA, and that acetyl-CoA will go into the Krebs cycle. Remember your Krebs? No? Okay. And what happens there in your Krebs? You produce ATP substrate level in the cycle itself, and then you produce NADH and FADH2, which is of course shunted to your electron transport chain to produce more ATP. However, in your glycolysis, you also produce ATP right away, and also reducing equivalent NADH. Now that NADH depends also now if there is oxygen or not, or deficient oxygen. Then if there's plenty of oxygen, then that NADH, just like the NADH produced in the citric acid cycle, goes into the electron transport chain. Okay? And again, the ATP formed in glycolysis is substrate level phosphorylation. So if you remember, in the initial reaction, glycolysis, your hexose, your glucose, is twice phosphorylated. First, by a hexokinase or a glucokinase, depending on which organ. Glucokinase is in the liver. Your hexokinase is in other tissues other than the liver. Okay? And then the second phosphorylation is by your phosphofructokinase. And after that, you form a fructose 1,6-diphosphate. It is cut into half, and then you will have 2 trioses. And that 2 trioses now goes through several steps in the glycolysis. And product is pyruvate. Okay. That pyruvate, as I mentioned earlier, will either become lactic acid or acetyl-CoA. It depends on oxygen again. If there is deficient oxygen, then we call it anaerobic glycolysis, and that pyruvate is transformed into lactate. And that is the end there, dead end. That lactate will accumulate until the time when oxygen is now insufficient, in enough supply or a sufficient supply. So that lactate reverts back to pyruvate, and that pyruvate now goes into the mitochondrion and will be converted to acetyl-CoA, becomes a substrate for your Krebs cycle. Okay? All right. So, I forgot to mention that the blood carries that glucose not to the cells, where it is transported across cell membrane by carrier molecules. And this process is facilitated by insulin. No? Insulin. And insulin, the target tissue of insulin is adipose tissue and the muscle tissue. And you should remember that the transport of glucose is not facilitated by insulin in red blood cell, intestinal mucosa, brain, and the liver. No insulin is needed. Your glucose can pass through the cells. Okay. All right. So your glycolysis occurs where? In the cytoplasm. And as we said earlier, it produces energy, and by converting your glucose into 2,3-carbon compounds, which are called triose phosphates. Okay? So, yes. Do you need to show that? You need to show that just as a reminder. Oh. So most tissues have at least some requirement for glucose. You have this already. Glucose requirement is substantial in the brain. Even in prolonged fasting, brain can make more than 20% of its energy from ketones. Heart muscles adapted for aerobic performance, has relatively low glycolytic activity and poor survival under conditions of ischemia. Diseases as a result of deficient enzymes of glycolysis, hemolytic anemia, and usually the enzyme there is pyruvate kinase. Fatigue is usually due to deficient phosphofructokinase in the muscle. Cancer cells are fast-growing cells and requires large amount of energy. Those glycolysis proceeds at a high rate, forming large amounts of pyruvate, which is reduced to lactate and is exported. Okay. We mentioned that cancer cells does not like oxygen. So they thrive in deficient oxygenation. Okay. And so their type of glycolysis is anaerobic, which is a very expensive way of producing energy. Because for every molecule of glucose, you have only a net amount of ATP. There are only two net amount of ATP. for every molecule of glucose in anaerobic glycolysis. You know that, no? Okay. So because of that, there is always your cancer cells like so much to be in an acidic environment because of the lactic acid that they are producing. That's anaerobic glycolysis. And they like so much sugar, or they like so much carbohydrate because that's the only way that they can get energy from carbohydrate. And carbohydrate, it's glucose. So one way to starve, to hinder the growth of cancer would be starvation of the cancer cells. Limit your carbohydrate. Okay? Okay, so it says here, muscles contract in anaerobic conditions, muscle glycogen disappear, and lactic acid accumulates. That's good, no? You know that why you will have lactic acidosis later on. And this brings about cramping of the muscles, of the skeletal muscles, when you have so much of lactic acid. When muscles contract in aerobic conditions, you do not form lactic acid. Lactate is oxidized in the pyruvate, in the mitochondria to carbon dioxide and water. That pyruvate is converted by your pyruvate dehydrogenase complex into acetyl-CoA. In yeast, microorganisms, pyruvate form in anaerobic condition. Lactate is not produced, but rather ethanol, because it is decarboxylated. One carbon is lost, and the two carbons forms ethanol. So that is fermentation. Okay, that's how it is. If you have this, look at this. This is the first, the triose phosphate is oxidized, and your NAD is the acceptor of hydrogen, and that NADH goes into your electron transport chain. Now, if this is blocked or there is oxygen, the hydrogen here is given off to pyruvate to become lactic acid, and you regenerate back this NAD so that you can have this reaction again. Otherwise, if you do not have any more NAD, they are all NADH plus H. Then that NAD is insufficient, or there are a few of these already. So there's not much. Uy, ano ako? Naglubat. Oh, okay. Naglubat. All right. Okay. So this is how it is, no? Now here, in this case here, pyruvate is decarboxylated and becomes alcohol. No, that's it. In case. Okay.
Loading. Loading pa.
Loading. Sino to? Uy. What happened?